Well, we're going to get into, we're first going to do section 4.9, finish out chapter 4. I'm going to do this again so we can catch back up. 5.1 will be extra credit. So if you are somebody who desperately wants to see more applications, then you should do those, the 3.1 and the 5.1 extra credits. Those are where you see the applications to currents and springs with masses on them and stuff like that. 4.9 is dealing with, I kind of set this up, I think, before. This is systems of differential equations, right? And there's one thing that is from a section that I made extra credit earlier, which was the 4.5, the annihilation stuff. One thing we're going to borrow from that, and we talked about a little bit, was how to write derivatives as operators. It actually makes the systems of differential equations look a lot easier to work with. I mean, it just makes it easier to work with. So a system of DEs, let's see, let's just take one out of here. Could look like this. Let's see. Yeah. Yummy. So if I have a single differential equation, then my answer is going to be a function, right? So like the dy dx stuff we've been doing. The answer was like y equals something. yc plus yp. Now what is my answer going to consist of?
X equals and y equals.
Yeah, it's going to have two functions, right? And they're going to be related to each other in some way. In fact, their constants have to be the same. They don't have to have the same, so one could be c1 e to the t, and the other one could be 3c1 e to the t, but they both have to have c1. You can't have c1, c2, c3, c4, not because we have to force it, but because it has to be true that they are related to each other, because they both work with each other. Does that make sense? So there's an easy way that sometimes works to make the constants just come out the same. And then there's another way that's not really that hard, but it's just annoying to get them separately and then try to make the constants work out between the two. All right. So I'm going to try to do it. Well, we'll see how I feel like doing this one. The thing with the way to rewrite this, so it looks a little bit more like what we're used to with a normal system of equations back in algebra, is to get everything that's related to, now in this case, this one's not too bad. Let me try to show you. Do you remember what dx represented before? Yeah, so this would be like, in this case it would be dx dt. dy in this case would be dy dt. Just because everything's in relation to derivative with respect to t. I like it. Okay. So I can write this first one as, let me call them A and B, or just 1 and 2. Dx equals negative y plus t, and dy equals x minus t. So you have two functions will be your answer, x equals and y equals, but in the equations themselves, you sort of have two layers of variables. X is different from dx. Y is different from dy, right? Okay, so let me just kind of show you the way this is going to work. If I wanted to kill, this dx, for example, right? I know what dx is. I could do two different things. I could do elimination and substitution. Let's try to stick with elimination. In fact, it's in the title of this thing. How can I make a dx show up here? What would I do to make a dx show up there? Yes, so I'm trying to do elimination, so I'm trying to make the same thing that's here. I'm going to subtract it so they don't cancel. You guys see this idea? In fact, let me write this a little bit differently. Let's say this is dx plus y equals t, and this is dy minus x equals negative t. So if I take the second one, and now here's the beautiful thing. If I take the second one and take the derivative of it both sides, so apply another d operator, right? Let's see what happens. So what's 2 going to look like now if I apply a d operator on 2? So this will become, yeah, I'm going to apply d by dt. I'm going to apply that twice to y, so that's going to be d squared y. And what does d squared y look like in our regular notation there?
D squared x
d squared y.
d squared y
d squared y over
d squared.
d squared. That's what that really represents. It's just too much crap to write down, so we take the operator notation. It makes it a little easier to keep track of stuff. Keep going. Minus dx. Careful. It's with respect to t. Equals now -1. So all I did was I took a derivative with respect to t. So it makes that one already had one, so now it's the second derivative of that. That one didn't, now it's the first derivative of that. That one's t, derivative with respect to t, and that is -1. I like it. So what can I do between these two now? How does elimination work? I mean, if I do what with these, the dx's will cancel. If I add them together, right? So if I add 1 and 2, what do I get? I get the dx's cancel. I get d squared y plus y equals t minus 1. What is that?